Hello, this is Ali Kotami with SCS Engineers. Thank you for taking time out of your busy schedule and listening to this presentation. The subject of the presentation is pressure testing of HDPE pipes using incompressible fluids and the impact of ambient temperature on the pressure testing. Pressure testing is normally carried out on solid HDPE pipes that are used for high pressure liquids passing through it, which could be a leachate force main, condensate force main, and gas well liquids force main, which could be a smaller force main extending from a gas well to a larger force main to a storage tank. In either case, the subject of this presentation is related to the pressure testing of these pipes using incompressible fluids, meaning similar to water. If air is being used for pressure testing, this material presented in this presentation would not apply. Normally the specification for pressure testing is put forward by the design engineer, and the parameters such as initial pressure, test duration time, and allowable pressure drop APD are specified by the design engineer. But there is another parameter that I haven't seen in any pressure testing specification, and that is the impact of ambient temperature in the final results of the pressure testing. And the subject of this presentation covers that angle of this specification for pressure testing. Ambient temperature impact could go in two different directions. If temperature increases, that causes expansion in the pipe, and as a result pressure inside the pipe decreases. This pressure decrease has nothing to do with pressure decrease due to a leak in the pipe or a leak in an extrusion valve or a butt fusion valve of the pipe segments. This is simply because of the change of volume of the inside volume of the pipe. On the contrary, temperature could decrease, which causes contraction, and the pressure inside the pipe increases as a result of the contraction. To show the impact of ambient temperature on final pass-fail pressure for evaluation whether the test was a failure or a passing result, you start with a pressure volume relationship. In this case, P1 times V1 equal to P2 times V2, which is basically tells you that the multiplication of pressure and volume is always constant. If the conditions change, meaning pressure or volume change, still the multiplication under the initial condition is equal to the multiplication under the final condition. As listed here, P1 is the initial pressure, V1 is the initial volume, P2 is the final pressure due to temperature difference, not any leaks or anything. V2 is the final volume due to temperature difference. If you solve this equation for P2, you will arrive at equation 1. P2 is equal to P1 times V1 divided by V2. Again, the leak from a defect or from a butt fusion valve or anything is not included in this model as I'm presenting to you until the very end of this discussion, that I will bring that into the picture. In this slide we show you the calculation of the volume inside the pipe under the initial condition and the final conditions. V1 being the initial condition volume may be presented as L1 times P1 squared over 4 pi, L1 being the initial length, P1 is being the initial interior perimeter of the pipe. Similarly, V2 is equal to L2 times P2 square over 4 pi, L2 being the final length of the pipe due to temperature difference, and P2 being the final perimeter of the pipe due to temperature difference. The temperature difference can affect the length, so the final length L2 can be expressed in terms of the initial length in the form of L1 plus L1 delta T alpha L. L1 being initial length, delta T being temperature difference, and alpha L is the thermal expansion coefficient in longitudinal direction of the pipe. A similar relationship can be written for the perimeter of the pipe, which is P2 is the final perimeter of the pipe, is equal to P1 plus P1 delta T alpha C, which in this case alpha C is the thermal expansion coefficient in circular direction of the pipe. Alpha C and alpha L are two different numbers, and their ratio is expressed as M. M is a value that is normally provided by the manufacturer. So alpha C could be written in the form of alpha L over M. M is an integer number and greater than 1. So that makes alpha C smaller than alpha L. So if we substitute equations 2, 3, 4, 5, and 6 into equation 1 and disregard terms that produce very small numerical values, we will arrive at equation 7. Equation 7 gives us the final pressure in terms of initial pressure P1, temperature difference of delta T, thermal expansion coefficient in longitudinal direction of the pipe, which is alpha L, and the M value, which is the ratio between the thermal expansion coefficients in the longitudinal direction and the circular direction. Since the parameters pressure and temperature can go either way, up or down, so we have to define some sign, mathematical sign for our mathematical operation. And delta T is defined as T2 minus T1, which is the final temperature minus initial temperature. If the temperature during the test goes up, so T2 is greater than T1, and delta T will end up to be positive number. But if we get a temperature decrease during the test, T2 would be smaller than T1, so delta T will end up to be a negative value. Similarly, delta P is defined as P2 minus P1, P2 being the final pressure after temperature effect, and P1 is the initial pressure. Again, if final pressure is higher than P1, delta P would be a positive value, and if final pressure is less than initial pressure, delta P would be a negative value. Now we arrive at the stage that the impact of temperature can be incorporated in the formulation. First, if we want to arrive at the pass-fail pressure at the end of the test without considering temperature, that would be equation 8, which is equal to initial pressure minus APD, allowable pressure drop, which we have been using in the field for many years without really considering temperature effect. If you want to consider the temperature effect, that would be equation 9. That would be P sub PFT, which is pass-fail temperature considering temperature, is equal to P1, which is initial pressure, plus delta P minus allowable pressure difference, APD. Delta P could be positive or a negative number. Now overall we have two cases. If delta T is less than 0, meaning we have a temperature drop. So it means we end up with pipe contraction, and we end up with pressure increase inside the pipe. Pressure increase meaning delta P is greater than 0, and as a result, pass-fail pressure considering temperature will end up to be greater than the pass-fail pressure without the temperature consideration. On the contrary, if delta T is greater than 0, we get an expansion in the pipe, pressure decreases inside the pipe, so delta P will end up to be less than 0, and as a result, pass-fail pressure considering temperature will end up to be less than pass-fail pressure without considering temperature. To clarify this, the concept of this formulation, we are going to go through a couple of examples. Here is the example 1. The data for example 1 is provided and listed here. T1, which is the initial temperature, is 90 degrees Fahrenheit. T2, which is the final temperature, is 115 degrees Fahrenheit. So there is a temperature increase in the field during the test. Alpha L is provided, M equals 3 is provided, and initial pressure P1 of 60 psi is also provided. The allowable pressure drop APD is set at 5% of P1, which equals 3 psi. And the question is, what are the values of pass-fail pressure without considering temperature and pass-fail pressure considering temperature? The solution to the first part of the question is fairly simple. Use equation 8 and we calculate pass-fail pressure without considering temperature by subtracting the APD, which is 3, from the initial pressure, which is 60, and we arrive at 57 psi, which means if the final pressure of the test ends up to be less than 57, so it's a failure, and if it is higher than 57, it is a passing test results. The second part of the question is related to the temperature effect. We start with calculating delta T, which is final temperature minus initial temperature. 115 minus 90 is equal to 25 degrees Fahrenheit. So delta T is a positive number. We substitute that number into equation 7. We arrive at the final pressure of 59.78 psi. From there we calculate delta P, which is P2 minus P1. And then we arrive at negative 0.22 psi, which delta P is a negative number. Substitute that in equation 9, and we come up with a pass-fail pressure considering temperature of 56.78 psi, which means if the final pressure in the field is less than 56.78, it's a failing test, and if it is higher than 56.78, it's a passing test. Consider, just for the sake of argument, if the final pressure was 56.9, under the first part of the solution, which is pass-fail pressure without considering temperature, would have been a failing test. But under the second part of the solution, which is pass-fail pressure considering temperature, would be a passing test. So it becomes important what numbers, what threshold your project has with respect to pass-fail. Example 2. The data for example 2 is listed and presented in this slide. T1 is 90 degrees temperature, which is the same as example 1. T2 is 70 degrees Fahrenheit, which indicates that there is a temperature drop in the field during the test. Alpha L is provided, M is equal to 3, similar to example 1.
P1 is equal to 60 psi, also similar to example 1. And the APD, allowable pressure drop, is also set as 5% of P1, which is equal to 3 psi, similar to example 1. Now the question is, what are the values for pass-fail pressure without considering temperature and pass-fail pressure considering temperature?
Similar to example 1, pass-fail pressure without temperature impact is 60 minus 3, which is equal to 57 psi. Same result as example 1. But for the second part, which is considering the temperature, we calculate delta T. 70 minus 90 is equal to minus 20 degrees Fahrenheit. So delta T is negative in example 2. Substitute that in equation 7, we arrive at P2 of 60.02 psi. We calculate delta P, P2 minus P1, we arrive at the delta P of 0.02 psi, which is a positive number, contrary to what we had in example 1. Substitute that value into equation 9, calculate the pass-fail pressure considering temperature, ends up to be 57.22 psi. This value is greater than the 57 at the top of the slide. Again, the pass-fail pressure considering temperature is different than the pass-fail pressure not considering temperature. Now here we present a comparison between example 1 and example 2 results. For the case of pass-fail pressure without temperature effect, both results are the same, which is 57 psi. So whether the temperature goes up or down doesn't really affect the results. It's always 57 psi based on the data. The second part shows the comparison of the pass-fail pressure considering temperature. The first line represents the example 1 results, where the temperature change was a positive value and the pass-fail pressure considering temperature was 56.78, less than the 57 value at the top of the slide. For example 2, delta temperature was a negative number and the pass-fail pressure considering temperature was 57.22 psi, which is higher than 57 psi. So it depends on which direction the temperature change is, positive or negative, the pass-fail pressure may change. A quick evaluation of the extent of this change gave me an idea that it's approximately 7% of APD. This 7% of APD may not come across as significant value. However, it may affect the result depending what outcome you get out of your test. Just to give you an example, I had a case 2 years ago in Miami at a site, which the result was a failing result based on the pass-fail pressure without considering temperature. But when we started looking into change of temperature, our results ended up to be passing results. We presented the data and our evaluation to the client, and the client agreed with us. We also communicated with the state regulatory agency in the same fashion, and they agreed with our approach and accepted it as a passing result. So the impact could be valuable to the final result of the test. With that, I conclude this presentation. Thank you again for taking time out of your busy schedule and listening to this presentation. If you have any questions, please feel free to contact me at my cell number 561-441-1473 or via my email. Thank you again.